Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's go ahead and get started, and I'm sure there'll be a couple more folks rolling in as time ticks down. It's my pleasure to introduce Ed Colgate and Michael Peshkin from Northwestern University today. Ed and Michael are in the mechanical engineering department, but Ed also co-directs the Seagull Design Institute with Don Norman out there. They've got an impressive slate of domains they work across, everything from human-machine interaction to robotics to telemanipulation and obviously haptics, which they'll talk to us about today. They've started numerous spin-off companies, most of which are amazingly successful. And they're going to talk to us about some of their work on surface haptics today, and then have a live demo, in fact, which is always exciting. So, Ed?
Thanks so much, Desney, and we really appreciate the chance to be here and to speak about the work we've been doing. So I'll do the speaking for the talk, but this is very, very much work that Michael and I have collaborated on here over the past few years, as we've collaborated on many things through the years. So yeah, the topic today is surface haptics. A lot of the work that we've done through the years is just haptics. And in the early days of haptics, a lot of it was sort of fundamentally occurring in 3 dimensions. So devices, probably many of you are familiar with devices like the Phantom, small robot that you can grab onto, sensors on it that tell a virtual environment running on some computer, where you are in that virtual environment. If you run into things, physics-based models compute the interaction forces. Those forces are fed back through actuators, and that closed-loop interaction creates a very, very compelling sense of physical interaction with that virtual world. But the world has changed a lot, and touchscreen devices like this one from Apple, but many others have really changed the landscape of haptics in recent years because the touch surface has become such a prevalent interface that all of us use in our daily lives in multiple instantiations. And so the challenge has been, down from that 3-dimensional world into a 2-dimensional world. How do you do haptics in a meaningful way on a surface? So I define surface haptics as providing programmable haptic effects on physical surfaces. And the real question that's driven a lot of our work has been, how do you do this? I'll give just a very, very brief review of some of the techniques that people have explored, and then really kind of focus on what we've been doing. Probably one of the most sort of time-honored approaches to this has been what's called by many eSTEM, which is the idea of actually driving a certain amount of current through the tissue in order to cause nerves to fire. It's really a pretty interesting idea. After all, the information that's traveling to your brain about touch is ultimately conducted along nerves, which are electrical signals. The difficulty of it is that, in fact, in your fingertip, you've got a whole constellation of different sorts of mechanoreceptors, 4 different mechanoreceptors responding to things like deformation or vibration or stretch, as well as raw nerve endings for things like temperature and pain. And the problem with this approach is that it's not very selective. It's very difficult to make it select out particular types of mechanoreceptors and generate particular sorts of responses. So this is a challenging area in terms of generating more natural interactions. An approach which is really the leading approach out there in the world today is vibrotactile. There's a lot of good reasons why one would use vibrotactile for providing haptic feedback. It's a very easy thing to generate from a sort of an engineering standpoint. Certainly there's a lot of room for optimization, but fundamentally generating vibrations is a pretty straightforward thing to do. But more to the point, we are very well adapted to feel vibration. Sort of a very famous curve I should have included in the talk that shows that around 250, 300 hertz, you can feel vibration amplitudes of 1/10 of a micron. It doesn't take much to generate a perceptible response. On the other hand, I've been told by some in sort of the neuroscience community that part of the reason we're so sensitive to vibration is that if a fly lands on your arm, you want to be able to swat it really fast, right? So this underlies the point that haptics is really a whole set of sensory and perceptual systems that have different functions. And a lot of those functions have to do with knowing when and where in your body you're in contact with the world, including flies and mosquitoes. And so there are other things that haptics is important for, like grabbing onto things, manipulating things, identifying objects by touch, and vibration isn't necessarily as important a part of those. What many people would consider kind of the holy grail of surface haptics is modulating the shape of the surface. So there's been a lot of work on things like pen arrays, deformable surfaces. Very cool stuff, but obviously very, very high level of technical challenge, and often doing this sort of thing has some sort of very deep incompatibilities with other sorts of things that you might want to do on a surface, like get light through it. So I'm not going to be talking much about this, although I think the long-term future probably these approaches have a lot of promise. So what I'll be talking about is the use of shear force. This has really been our focus. This is probably the earliest example I know in the literature of using shear force for haptics. This was a device where there was literally a transparent cover on top of a display and actuators that would tug on that cover. And it's sort of very much a conventional type of force feedback haptic device. Not necessarily very practical, as something that could be implemented in many different settings, but sort of a very clever idea. This was from 2004. Following that, not a lot of work was done on doing shear force. I suspect because of the difficulty of doing this, generating these forces on the bare finger. I'll come back to that in a moment. But there are very deep reasons why shear force is an important thing to do. One of the very early and best known pieces of work in the field of haptics was Margaret Minsky's, Margaret was Marvin's daughter, development of the sandpaper system, work she did at the MIT Media Lab in the late 80s and into the 90s. She took a force reflecting, a force feedback joystick that can move only in the plane, but program various force effects in the plane, and was able to demonstrate that people could perceive textures, if you will, that sort of had the perception of bumps or ridges that would penetrate out of the plane. So even though the motion was only in the plane, people would perceive a three-dimensional interaction. Then Vincent Hayward and his student Gabriel Robles de la Torre took this further in a very carefully controlled study that they published in a Nature paper around 2001. And what they demonstrated was really pretty cool. They had people literally moving over bumps, not actually feeling the local shape, so their fingers were on a flat object, but the object was moving up and down and following that bump contour. Then they had people moving in a perfectly flat plane, but playing a set of forces that were essentially the reaction forces one would feel from traversing a bump. Both cases led to the percept of a bump. But then they combined them. Actually, they took the physical bump and turned it into a hole, but kept playing the force percept of the bump. And the really amazing result is that the force percept could be strong enough to overwhelm the percept coming from actual up and down motion. So you'd feel a bump even though you're physically moving down through a hole. Sure.
How would they implement the force percept?
This was done also with a kinesthetic force feedback display.
Flat surfaces up and down?
No, in this version, what they were doing was very much what's shown here, a mechanical device that would literally move up and down, but no force feedback. This was done with force feedback using motors, a closed loop system that would only in plane, right? And then they combine the two. So pretty important in that it shows the existence of a haptic illusion that's really quite powerful, right? That you can perceive shape, three-dimensional shape, based on a pattern of forces in space. So these are pretty cool and to me very inspiring, but again they both dealt with systems where you were grabbing onto or being bound to a device. And the challenge really is, how do you do this on a bare finger? Right? That's the challenge that Michael and I have been working on over the past few years. How do we control the shear force vector acting in the plane on a bare finger? So here's how we approach that problem. We use friction. it'd be nice to think in terms of, what are all the different physics you could appeal to for pushing around a finger. It'd be great if your finger was, was magnetic and you could essentially build a linear motor. But really what you've got to play with, as far as I know, is friction. So I show this classic equation of kinetic friction, the Coulomb model of kinetic friction, which is almost certainly wrong. For instance, your finger being deformable has a nonlinear dependence upon normal force. But I don't really care about the details right now. What I care about is the constituent pieces. Okay? They are coefficient of friction, normal force, and relative velocity. How slippery is that surface you're contacting? How much normal force is there with that surface? And then what's the relative velocity? These are the things that we can potentially manipulate in order to control that force vector. And we've been working on all the pieces, so I'm going to kind of break this down into the pieces. And then we'll show you demos at the end of essentially all those pieces. So coefficient of friction was really where we got our start. We kind of stumbled into this, a grad student discovering that putting a finger on a vibrating surface, that surface felt more slippery. It turned out other people had been seeing that as well. Back in '95, Watanabe Fukui published the first paper in this area in which they used a big old ultrasonic horn vibrator to cause a plate to vibrate, and they put sandpaper on it, and when vibrating at 75 kilohertz, so way into the ultrasonic range, people still felt that sandpaper getting less rough. And others have worked on this as well. What we've done is take that and build something we call the TPaD, where we've integrated those ultrasonic out-of-plane vibrations with a glass surface, and we can take this glass surface and make it more or less slippery. And this is one of our prototype devices. Just to explain a little bit more about how that works, this is supposed to be a movie, but I think I don't have it set up quite right, so I'll just talk over it. What we're looking at here is actually a measured profile of the waveform, or the mode shape of a piece of glass that's vibrating at a resonance measured with a laser Doppler vibrometer. So there's a set of piezoelectric actuators glued to the glass over here, and we're exciting those things, causing the glass to bend, and then doing that at a resonant frequency that has this particular mode shape. So basically every point on the surface is kind of moving up and down, and one brings the finger down on it. And so the surface is basically bouncing up and down against the finger. And an interesting question is, why does that cause friction to go down? And there's a bunch of papers in the literature, including ours, that claim that the mechanism is this. I'll show you in a moment that it may not really be. But it's like this. Imagine that this upper plate represents the finger, and this is the plate moving up and down. There's some air in between. And air has both compliance and air has viscosity. And both are nonlinear effects. They are nonlinearly modulated by the gap between the upper and lower plates, so that as the lower plate gets close and squeezes the air, the pressure peaks at above atmospheric. So this dashed black line would represent atmospheric pressure. You get a pressure peak, but of course you're trying to squeeze that air out. On the other hand, the gap can get quite small, so viscous effects can become pronounced. And we're talking about gaps that are sub-micron here, so really quite small. As it moves away, you get a larger gap. Pressure drops below atmospheric. On the other hand, the gap gets large, so it's fairly easy for air to flow in. And the net of this is that it acts like a pump and pumps a bit of air in between the plates, and the average pressure goes above atmospheric. And so you're riding on an air bearing. At least that was sort of the theory. We've recently been able to take data using a laser Doppler vibrometer that suggests it's not quite right. The actual data we took is represented down here in the black. The solid black line is the velocity of the surface. So this is a surface vibrating at something like approximately 25 kilohertz. And then the dashed line is the velocity of the finger. And the thing to note is that it has this very precipitous drop, followed by a little phase where the velocities are almost matched. And so if you integrate this data, you get data that looks like the blue up above, displacement data. The thing is, there's always an offset of integration, and so these two blue lines, we don't really know where they are vertically relative to one another. So what we've done is just slid them up to where we think they ought to be. And based on what we're seeing here, it sure looks like contact occurs, because we've got this little area where there's this precipitous drop in velocity followed by kind of a tracking. So it actually looks like contact is occurring, and the finger is then essentially bouncing off the surface. So we've done a bit of modeling and analysis with that, and indeed there's a very good reason to think that that would have the effect of reducing the apparent friction coefficient. In fact, the behavior becomes a bit more like a viscous relationship as opposed to a Coulombic friction relationship, but with a very low viscous coefficient.
Since the finger is squishy, how do you measure the position of the finger?
What we're doing is we've got this piece of glass that's sitting here vibrating. We bring the finger up underneath it, and then we use like a silver Sharpie to make the finger a bit reflective and look through the glass right at it.
It's really the finger.
It really is the finger.
The pad that you're seeing.
Yeah, which has been sort of nicely flattened out because of the fact that it's touching the glass. Yeah. So I might say a bit more about that in just a moment, but those are the sorts of profiles that we see. So again, apparent contact. We also make friction measurements. So we have a little rig where we measure normal force and shear force, and we can relate the ratio of those two, the friction coefficient, to the amplitude of motion measured, again, with that laser Doppler vibrometer. And you see is very marked relationship. I mean, it's really a pretty impressive effect. If you start when things are off with a coefficient of friction of a mu of about 0.5, it drops by about an order of magnitude over a reasonable range of motion amplitudes. Feels very nice as well. It's very nice, slippery, air-bearing feeling. You can also turn it on and off really fast. So here's some data where we've got the normal force and frictional force both measured with the rig, and then we suddenly turn the device on, and that apparent coefficient of friction drops down significantly. You notice here an even higher coefficient of friction while the device is off. That varies a lot with both individual and with the preparation of the glass surface. So here it's close to 1, but again, drops down to something quite small. Not only that, you can modulate the effect. You don't have to have friction just on or off. So here we're trying to generate a sort of a bumpy feeling on a surface, and you see that indeed the friction coefficient is not smoothly modulated, but certainly not just on-off either. So we can generate some kind of nice effects that way. There are problems with this approach. One problem is audible noise. So you get this surface that's vibrating up and down. We try to operate in the ultrasonic regime so you can't hear it. And so this is frequency response looking at the motion of the surface itself. It's quite beautiful. All the energy is here at, in this case, 26 kilohertz. Can't hear that. But when we look through the glass at the finger, we often see things like this, where here's the frequency of the glass, and now here's the frequency of the finger. So what's going on there? Well, if you go back and look in the time domain, you see things happening like this. So same thing I showed you before, a little greater amplitude of the glass, and suddenly you see the finger skipping a beat. So we're getting a subharmonic. So now that most of the energy of the vibration of the finger is at half the frequency of the glass, and so it's a period doubling phenomenon. So your finger is acting like a little loudspeaker, generating noise at an audible frequency. So this is a bit of a problem. The thing that's kind of interesting here is that you'll see, I don't know if I've highlighted that, let me see. You see period doubling, but you also see this effect here where without apparent contact, the motion of the finger kind of turns around and departs from the glass. So why would it do that? Probably because there is in fact a squeeze film as well as contact. So this is a bit of an issue. It's a difficult problem to solve. It's an area of ongoing research. Frankly, the most pragmatic solution is simply to increase the frequency of excitation of the glass surface even more. That does come at some cost of energy. So an interesting problem. So just to summarize, we can generate some very nice high-quality haptic effects by making surfaces more slippery. It is difficult to eliminate these subharmonics. We can just operate at higher frequencies, but I suspect that there's more elegant solutions out there waiting for us. Okay, so now let me talk about normal force. So that was kind of how we make things more slippery. How can we modulate the normal force? Well, the main technique that we and others are using here is electrostatic. And two of the demos that we brought here today are electrostatic devices. So those who have been following haptics in recent years have certainly seen things from the Finnish company Senseg, and more recently from Disney Research Labs, the Tesla touch device. And these are operating electrostatically. The idea is pretty straightforward. It's to take a conductive surface, apply a potential to it, have it covered by some dielectric insulator, and then bring the finger down on the surface. The finger essentially acts as the second plate of a parallel plate capacitor. The plus and minus charges develop. They attract one another. You get a normal force. And then that normal force can be turned on and off as the finger moves in order to generate the sensation of vibrations. You know, a lot of people ask, gee, can you really generate very much normal force this way? And it turns out that in principle you can. So this is sort of the classic equation of the force that develops in a parallel plate setting, where A is the area of the finger in contact, V is the applied voltage, D is essentially the gap, the thickness of the dielectric here. This epsilon is the relative permittivity. And using reasonable values, you can come up with an estimate of normal forces on the order of up to Newton, and maybe even a bit greater. So that's not bad. If you have that much normal force to work with, and you have coefficients of friction that are on the order of 1/2 to 1, that means you should be able to vary the lateral forces by up to 1/2 a Newton or a Newton, which is a very significant effect. But if you actually look at the devices, the ones I showed before, I don't think you're seeing nearly as much variation in normal force. And a big reason for that is that your finger leaks. Leaks charge in particular. So if we look at the finger, it has the properties of a dielectric, but it also has the properties of a resistive, conductive material. So it has finite resistivity. So although there's a lot I don't know about the nature of, say, the charge carriers and so forth, charge does literally leak through the finger, and once it's through, it's going to end up on the surface. So that the electric field acting on those charges is no longer pulling on the finger, it's pulling on charges that reside on the surface. And so that means that the forces on the finger decay. And so what's important is the time constant of that decay. And so we've made some measurements that suggest that that time constant can be as short as 100 microseconds or less. And that helps explain why, even though in principle you might get fairly large forces, in practice, if you're varying that force at, say, 200-300 hertz, a lot of the time, not much is going on. And so on average, the forces are lower. So we've done a fair amount of work, which reflects itself in these prototypes, to counteract that effect, primarily by using an AC technique. Another thing that I know, I didn't put it into the presentation, but I know is of interest to some people here, is that these previous devices have required grounding the finger, and that's sort of a very practical issue. And so you'll find that we've also done things a little bit differently in order to eliminate that problem, so that no longer is it necessary to do what I'm showing here, which is directly ground the finger. So we've done these things because our interest is not so much just in generating the sensation of a texture or vibration. That's a worthwhile goal, but as I talked about earlier, we're very focused on this shear forces, these lateral forces, so that we can do force feedback. And we'll sort of say more about that later. But if you really want to do force feedback, then you really want to be able to generate significant forces. And for that, you really want to achieve as close to the sort of theoretical maxima as you can. This is some data that we've taken that show that, in fact, we do pretty well. Here's yet another very different friction coefficient. This is an individual, Xiaowei, with slippery fingers on slippery glass. And so when everything's off, he's got a coefficient of friction in this particular case of about 0.15. We rarely see things that low, but he must have gotten a whole, I don't know what was going on that day. But when we turn the effect on, you see a significant, in this case, about a 50% increase in the effective friction coefficient. So that means that the normal force is being increased by about 50%. So a pretty significant effect. And we've got lots of data like this. One of the issues that we run into is that it varies a lot across individuals, but we can pretty much always generate a significant effect. So we will show you some demos of this, but the use of electrostatics to increase normal force has a lot of virtues. It's very fast. We turn this effect on and off more or less instantly. It consumes very little power. I didn't actually mention the nodal lines, although I showed them in that waveform that I showed the modal shape of our vibrating surface. And those are areas where we get less of an effect with the friction reduction. And then I mentioned the noise issues. Those are gone here. So we have a very nice, simple system. The size of the effect needs to be studied further. I've talked a lot about that. We want to maximize it all that we can so that we can actually use this to generate big lateral forces on the finger. And then the other thing is that we're increasing friction rather than decreasing it, so the aesthetic of it is very different. And I would say on the whole, not quite as pleasing. Maybe not a very big deal the way that we intend to be using it in the future, which is to actually push the finger, not just resist it. And so let me now talk about that. So this, to my mind, is the really exciting part of all this. So I've talked about mu and n, but the thing is, friction forces are dissipative forces, right? So friction is always acting to resist the relative motion between the two surfaces. And so everything we've talked about so far, the direction of the force is always opposite your motion. And that's not satisfactory if we're really trying to do force feedback. We really need to be able to actively control the force on the finger, have it actually push the finger, have it push in different directions. If I want to simulate sliding along an edge, well, my velocity is parallel to the edge, but the normal force is primarily perpendicular to the edge. And I really would like to be able to do something like that. So I'm left with no choice but to move not just the finger, but the surface as well. That's the really big idea here, is how can we actually move the surface so that we can turn this resistive effect, this dissipative effect, into an actuator. And so we've developed a few devices that do this. The first was something we called the ShiverPaD, which has sort of a complement called the SwirlPad, and then more recently something we call the LateralPaD, which we have here. The idea is pretty simple. It's to vibrate the surface and then to synchronize those vibrations with levels of friction. At least that's what we do with the ShiverPaD, which we're showing here. So here we're showing how we would generate a force to the right, and basically we make it high friction as it moves to the right and then low friction as it sort of slips back under your finger. And then the idea is to do that fast enough that you don't perceive the underlying vibration, you only perceive the average forcing. And so with ShiverPads, we were able to do this up to about 850 hertz, which is fast enough that you don't really feel it. You have some amount of sensitivity at 850 hertz, but not much. We were not able to go at a higher frequency because it takes time to turn on and off friction. The way we were turning on and off friction was by using these out-of-plane vibrations. It takes time to build those up and have them decay. But it does work. I'll show you a little bit of data. These are some of the early prototypes. This was a TPaD, the device that vibrates out of plane, lets us control friction, and then it was hooked up initially just to a speaker and then eventually to a voice coil in order to cause it to vibrate side to side. And this is data with it vibrating only at, say, 40 hertz, but just showing kind of that, in fact, it really does work. We have periods where the TPaD is on and it's very low friction, so your forces here are very close to zero, and then periods where it's off, and so the forces are much higher. And so the blue line is an average force, which you see in this case is almost 100 millinewtons, which is really pretty significant in terms of generating haptic effects. So the idea then is to synchronize this with a knowledge of where your finger is in order to generate force feedback effects. So I'm going back to things like those bumps, those virtual bumps from the Hayward and Robles de la Torre that I showed you earlier, where they were showing that these in-plane force fields generate the perception of bumps or holes out of the plane. And so that's what we're trying to do here. And this is now actual data. Up here is actual force data, and here it is integrated, because when you integrate it, you get essentially a potential function, and the shape of that potential function gives you a sense of the percept. So this is the percept of a bump, the percept of a hole. The way we do it is we measure the finger's location, and then we modulate the direction and amplitude of the force to generate the corresponding force profile. So this is kind of a restoring spring in black, and the green is a unstable spring, if you will. And then you can begin to put those together and do things like this. The toggle switch, this is sort of my favorite little effect, where we have two line sinks, kind of holes, if you will, separated by a line source, a bump, and again, actual force data taken here and integrated to give you the potential function. So you see two potential wells separated by a potential hill, and so the idea is that your finger is going to kind of go pop, 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 as if you were walking into the room and flipping a light switch, which of course here you don't have such old technology, but you know what I mean. So this is sort of my favorite video that we've taken. It's hard to do these things to see haptics in a video, but I think you can see it here. You can see the finger pop, 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 back and forth. And really a pretty compelling effect. So to me, this is kind of what it's all about, is generating these closed loop force feedback experiences, dramatically different sorts of interactions than you're capable of doing with, say, just vibrotactile. But still pretty clumsy device, vibrating at 850 hertz, makes a pretty annoying noise. We were very interested in doing everything in the ultrasonic frequency range. And so that led to the LateralPaD, where what we were doing is synchronizing in-plane and out-of-plane vibrations, both at ultrasonic frequencies. So we have the demo here today. Basically what we've got is a piece of glass here. Looks kind of the shape of a microscope slide. We've got a couple of piezo discs glued to it, and when we activate that, we cause it to bend. The mode shape of bending is shown here, so basically it's moving up and down a lot in the middle where you put your finger. And then we pull these piezo discs out of these old Tide Buds ultrasonic spot removers we can get really cheap, and we throw them on the ends here. And so we have these piezo stacks here and here, and they are reacting against these end masses and causing the whole glass to move side to side. And again, the mode shape is shown here, so a lot of side to side motion in the middle where you put your finger. And then we tune these things to resonate at essentially the same frequency, and then we drive them with the same frequency, but we control the phase relationship between the out-of-plane and in-plane motions. And when you do that, so you can kind of imagine that the surface now is not only going up and down, but also side to side, and so it's kind of making elliptical motions, this way or that way. And by controlling that phase relationship, we can control the lateral force quite well. And so here's the relative phase between the two, and this is the lateral force coefficient, which is lateral force divided by normal force. You can kind of get a sense of the scale of the effect by thinking about this vis-a-vis friction. It's not friction, it's active, but with friction coefficients of about 0.15, how sticky is such a surface? Well, that's about how strong this surface drives, which is not as strong as we'd like. We'd like it to be about double this, but I think you'll find that you can feel some pretty cool effects. So we do much the same sort of thing. One thing that we were very interested in is what motions of the surface are actually creating the largest forces, and so we made some measurements using, again, a laser Doppler vibrometer, looking both straight down at the glass, which gives us the up and down motion, and then tilting the glass so that we're able to measure some component of the sideways motion as well. And then once you run through the math, what you find is that the motion of the glass that generates the largest forces on the finger are when the up and down and side to side are in phase, which basically means that the glass is coming up and hitting the finger in these little pulses like this, which is exactly the same thing that TPaD, the friction reduction device, would do. It's moving straight up and down, but as you move this way, you sort of tilt that angle in the frame of the finger. And so this is sort of tilting it without the finger moving, and so it generates steady forces on the finger. We can do the same sort of things to generate virtual bumps. Again, actual data taken. The forces in this case are up to about 50 millinewtons, so only about half as strong as that ShiverPaD. So again, a very active area of research is how do you make this effect stronger. So to summarize, this is really the key part of it. We've more or less proven that that these coordinated effects work, but there's a fair amount remaining to be done in terms, especially of increasing the force levels. So those are the big effects. I will shut up now. These are some of the wonderful students who've really done all this work. We've had some great collaborations and support from the NSF as well as Department of Transportation and Ford. And so I think now we can take questions and run demos. So I'm going to move this over. Well, questions.
What application is this? Are you doing touchscreens for automobiles or for handheld devices or all the above, or just generic haptics?
Well, I think as you can kind of see from the nature of the talk, we're more interested in kind of the enabling technology. That's kind of our strength, and so part of the reason that we collaborate with people, we're hoping to start collaborating with Hong, and Karen McLean is someone who looks a lot at human-computer interface. So we're starting to do those things so that we can begin to sort of get feedback in terms of understanding what the needs of the applications are. So I guess the answer is that we're somewhat agnostic, but we're trying to learn more. And I guess one of the reasons that we're here today is to try and understand what vision you may have in terms of haptics and how it can have an effect. But I do think that having spent a lot of years of my life studying haptics, that I feel very, very strongly that that this paradigm of doing force feedback, whether we've optimized it or not is another question, but this paradigm of doing force feedback is immensely more powerful than the paradigm of vibrotactile, and therefore I think very worthy of being developed for applications in all these arenas.
Let me just add to that for mobile devices, which is a very attractive market, power is of course an enormous concern, and our piezo devices are pretty high power devices, and they'd have to be reduced by orders of magnitude to be sort of in the ballpark for mobile devices. But the electrostatics are closer, better.
Yeah.
Can you speak a little bit about efforts to localize the force feedback to a specific area? Because it seems all of these devices seem to function on the whole plane, right?
Yeah, it's a great question. So we have plans for we have a pathway toward localizing it. I'd say the one technology that doesn't necessarily act over the entire plane is the electrostatic. Right? Things that involve the mechanical vibration, it's pretty tough to build something where you can really localize the vibrations without consuming even more energy. But the electrostatic's not a problem there. So that's really the key enabling technology. So I didn't say it here, but really our path forward is combining the electrostatics with the in-plane vibrations. Go ahead, Michael.
I just wanted to make absolutely clear that when you're working with one finger on a surface, because you can read the position of the finger, you can make it as if you had localized the effect. But as soon as you've got more than one finger, or, as you were saying, if you want to conserve power, it'd be really nice to actually localize make it different on different parts of the plane.
Imagine trying to pull your fingers to the home row of the soft keyboard. You've got 8 fingers now, thumbs in the space bar, but in the wrong spot. If you could snake each finger to the right spot, that would be very, very interesting. But that sounds very difficult.
Interesting.
I wouldn't write that off. I mean, it's a deeper discussion of how you do that, but I think the key is that the electrostatics can be localized, and that's probably all that you need if you can get the vibrations right.
We in developing, I come from the product development group. Well, we in development looking for haptics for mice and keyboards, direct and indirect touch devices, all these things. We looked at a wide variety of haptic devices, but what we're generally trying to do is imitate dome switch clicks. Mm-hmm. Other sensations that don't require your finger or don't expect your finger to move laterally. You coming down on something, pushing down. So we've had Sensei come in, we've had Tesla Touch come in, mm-hmm. and the effects are kind of neat when you stroke across. Yep. Especially they'll put it into an emissive display, so you stroke across a tile or something, and you feel it. has always been interesting, but not really appropriate for our applications because we're not stroking across anything. Our fingers aren't moving anywhere in our applications.
Right.
What's quite interesting about this is your finger looks like your finger can be in one spot and will feel a lateral force.
Yep.
That gets really quite interesting in ways of giving cues to your finger that it's in the wrong spot, say if you keep on actuate a soft button.
Yeah.
Right, which makes it more likely to be applicable for an eyes-free interaction.
Absolutely.
Right, that's the thing that's always been funny about
For a
for
what?
eyes, what we call
Eyes-free,
eyes-free interaction, right? So you don't want to take your eyes off the road while you're
Texting.
doing whatever.
Yes.
Yeah.
Yes.
And you know, as we get away from more and more, we get flatter and flatter user interfaces with keys that don't move anymore, and we want to preserve this sense of precision when you get your fingers in the right spot. There's nothing more frustrating than a smartphone with a soft keyboard. Period. I've never really experienced a good one.
Right.
Our own.
Right.
Sorry.
So we do have a demo of a soft keyboard, well, soft keys, I think 4 keys. And again, I'll emphasize that the level of forces isn't where it really needs to be, but despite that, I think you'll find that, especially sort of after just a little sort of learning period, it's quite remarkable because the way we do it, we create these potential wells. So not only is it a steady force, but it's really trying to stabilize your finger at the center of the key. I find it personally to be a pretty compelling effect.
Yeah, that would be interesting to see.
Oh,
Sorry.
no. There's been a hand up behind you.
No,
I think.
I got something to this.
Have you thought about, since you're exciting with a coherent source, you ever thought about setting up X and Y standing waves for changing the vibration amplitude at different spots? That way you can target it. So it's like an acoustic hologram.
Yeah, I think I understand what you're saying, and to some extent, and Michael, you may want to chime in here, but to some extent, that's what we do. These vibrations are standing waves. They are resonances, if you will. We really try to operate at resonance because it's very efficient, right? What some people want us to encourage us to do is look at ways of exciting from the corners and focusing energy at certain spots. We have not put the energy into that. It's interesting, but I suspect my visceral sense is it's not going to be the thing I want to put my time into because I think it's going to be very, very difficult to avoid a significant amount of energy and lower frequencies. And then in general, it's not going to be a very efficient approach. So rather, what we've done is what I think Michael mentioned earlier, which is we measure where the finger is, and then we control the effects. The effects might be happening over the entire surface, but if you know where the finger is. But
guys from Berkeley, right, have that table where they use drivers in the corner.
for manipulating parts, right?
Well, they have the ability to move 2 or 3 pucks
Yes.
on the table simultaneously.
Yeah.
But when you play back the video, right, I don't think they quite have the audio.
Oh no, they're working way down in the audible realm.
The MEMS community do that for self-assembly.
Yeah, we have a colleague in Northwestern, Kevin Lynch, who does that sort of work too. You can go online and see videos of something they call the PPaD, which is super cool, where they vibrate not only into plane, but they do some little tilting action as well, and you can create some very, very nice force fields or velocity fields for parts. But it's hard for me to imagine those things working in our realm. I think it's very critical that we get into the ultrasonic regime. Certainly you must be above where you get that tactile perception. And you can get some perception up to kilohertz or so you've got to be above that. But then once you're there, it's very difficult to not be coupling energy acoustically, and so getting into the ultrasonic regime seems to be very, very critical. The other thing I want to say is our path really is to integrate this motion and to get rid of these motions. These motions, whether you hear it or not, are coupling into the air and throwing energy out there, and it's just not an efficient way to do things. So really the pathway forward is to combine the lateral motion of this device with the electrostatic control of normal force from these devices. Okay, and that's the thing that will enable us to, I think in a very power efficient way, be able to control, and also in a very authoritative way, control forces on multiple fingers. That's the focus.
Have you had trouble building structures that resonate at those higher frequencies? And the reason I ask is we tend
to use not piezo stack piezos, but bar or disc piezos.
We do.
Which are not as stiff, I think, as the stack.
So if you find trouble,
Well, I can't get there.
yeah, we can get there. We can get there. It takes modeling, and there's a fair amount of practical and issues. But actually, when you look at the demo in the middle there, you'll see both stack piezos moving this thing laterally, and also disc piezos, which are placed at the right spot, done or estimated computationally, in order to flex the vertical vibrations are done by flexing the surface, and then it goes into a wave motion.
With discs?
With discs,
So
yes.
they're glued right up against it, so they do the bat ray thing.
It's not exactly the bat ray thing, but they curve. They try to contract and they bend the surface.
Okay.
You're contracting it when it's glued to the surface, so it causes bending.
Okay, I think that's what I meant by the bat ray thing, because we put a little piston thing in the middle of the disc, and we push up and down.
That would do it too. This is done just with.
But we're not bending, but we have bent by gluing the whole thing against the surface.
Right.
So now as it contracts.
So that works. Actually, we've done very well with it. Not only with like fancy piezos, but just with these, things that are used as piezoelectric buzzers. Just total junk piezos. Even those, if we glue them down, we can put the glass into a resonant mode, into a standing mode.
Oh, resonance is essential.
Well,
your static displacements are
Less than a micron.
What we've been actually trying to do is to vibrate surfaces in arbitrary ways, is try to avoid resonance.
Well,
because resonance is getting in our way, we want to make a nice little
but
and we end up with a ring.
But you're vibrating in a frequency range where you want the person to feel that waveform.
Absolutely. So, but I get exactly right. So, but what we found is as we're trying to move the resonant frequency up, using piezo discs and fairly heavy glass stops, we get to 300, 400, 500 hertz, and we have a really hard time getting any higher. So I'm just thinking your application is different, but the structures are similar. I don't know how you manage to get up into the tens of kilohertz resonance when we can't get past 400 or 500. I'm thinking maybe it's because your piezo stacks are so much stiffer than our...
I think I know the answer. I think you can do it just as well as we can. The issue is that we're looking for only a micron of motion, because we're not trying to generate anything that you actually feel.
Okay.
We're trying to modulate this slipperiness factor. And you're trying to generate things that you feel.
Right.
So it's a different goal.
Wanted to actually, Carl, challenge you.
How would make it high resonance? Because the stuff's so heavy.
Yeah, well, at high frequencies, of course, moving any significant distance would be an enormous amount of energy just physically in the glass.
Right.
And there's nothing you can do in efficiency that's going to change that. I just wanted to go back to your earlier comment about sort of clicking and finding your place. I find that idea of home keys pretty exciting. But I'd hope that as glass becomes more interesting, as soon as when you have the ability to maybe individually drive your fingers around, that this kind of interaction with the glass becomes just one of many, many user interface pictures. I mean, we see that a little bit even for text entry now with things like swipe. But I have no idea. I mean, this is what you guys are really good at, is what could be the new ways, what could be the ways of haptic user interface that you could have once you have the ability to push you around.
Sorry, you had it.
Have you thought about experimenting with different textures of glass, albeit static, but that close to the display, you can get away with fairly large RMS modulation of the surface of the glass.
You mean the actual texture of the glass?
Correct. The static texture of the glass.
That's something we would like to do a lot more with. One of the struggles for us is we're basically a robotics lab that's been sort of slowly coming up the learning curve on things like thin films and material processing, and so we definitely end up with different textures of glass, not necessarily by intention. So I think everything here today is pretty smooth, which isn't necessarily what we really want. When it's smooth, that tends to promote stick-slip phenomena, which affects the mechanics of the interaction. So there's a lot of work to be done there.
not only can you vary the surface texture, and rough surfaces tend to be lower friction than the very smooth ones, but there are also oleophobic glasses, and there's all sorts of amazing stuff that these people can do on the surface of glass that are mysterious to us.
Let's do one last one, because I
One
think
more
we're all
thought,
sort of itching
what's
to get our
your-
fingers on this thing.
What's your theory on, say, electroactive polymers, which some people think is the clue to future haptics once the dynamic range is increased?
Well, I think they'd certainly have a role. But it's not, the way I parse up the world isn't so much whether you're using EAPs or piezos or electrostatics in order to do your actuation. The way I parse the world is, what are you doing with your actuation? And I guess my message here today is, don't put your stock in vibrotactile, okay? Put your stock in force feedback, because I think that from the standpoint of haptics and what we do with it in the world, the sorts of effects that we want to generate are ones that are based upon closing the loop with force feedback. So if you can use EAPs as part of a force feedback system, which I think you can, then absolutely. But so that's just sort of my parsing. All right, we want to show some demos. Thanks. So.